Let's now solve a few problems based on Cauchy integral formula and some of its very powerful corollaries. So, the first problem is to evaluate the following integral. Evaluate integral of e to the power z minus e to the power minus z by z to the power n over gamma, where n is a positive integer and gamma is the unit circle. It's e to the power it for t in 0 to 1. The integral a priori looks quite complicated to compute, but now we have some really powerful tools at our disposal. For example, we will be using Cauchy integral formula to evaluate this particular integral along the curve gamma. So, let us look at a solution. Let us call f of z to be equal to e to the power z minus e to the power minus z. The first thing to note is that f is an entire function, and because of that, for z0 equal to 0, if you look at d01 bar, this is certainly contained in the domain of definition of f of z. And recall, by the higher order Cauchy integral formula, the nth derivative at a point z0, in our case our z0 is just the origin here, this is going to be equal to n factorial by 2 pi I. So, maybe what can be done is we will focus on f n minus 1 at 0, this is going to be equal to n minus 1 times factorial times the integral over gamma of f of z by z minus 0 is z. So, this is going to be z to the power n minus 1 plus 1, which is z to the power n dz. If you notice, this is precisely what we were trying to compute here, isn't it? So, we are in good shape, because hence we have the integral of f of z by z to the power n dz over gamma. This is equal to 2 pi I times the n minus 1th derivative of f at 0 by n minus 1 factorial. This is precisely what we get. Now, computing this is going to be easy, the right hand side. Since f is e to the power z plus e to the power minus z, or rather minus e to the power minus z, we have f prime of z is equal to e to the power z plus e to the power minus z. F double prime is going to be e to the power z minus e to the power minus z, and so on. So, basically fk of z is going to be equal to e to the power z minus e to the power minus z when k is even, and it is going to be e to the power z plus e to the power minus z when k is odd. And therefore, the evaluation of fk at 0 is either 0 or it is going to be 2, based on whether it is even or odd. So, now getting back to what we want, this is precisely what we have, and therefore, integral of e to the power z minus e to the power minus z by z to the power n dz over gamma, this is equal to n minus 1 factorial, fn minus 1 of 0, 2 pi I. It is going to be 0 when k is even, because fk of 0 will be, one has to be a little careful here, it will be n minus 1. So, let me just write down the equation so that there is not going to be any mistake. This is going to be 2 pi I times f n minus 1 of 0 by n minus 1 factorial, and that will be equal to, when n is odd, we have n minus 1 is even, and therefore, it will be 0 when n is odd. And when n is even, n minus 1 will be odd, f n minus 1 of 0 will turn out to be 2, and this is going to be equal to 4 pi I by n minus 1 factorial. So I think I have not made any mistake here. Let me be a little careful. 2 pi I by n minus 1 factorial. The fn will also turn out to be equal to 0. So yeah, I think this is the correct answer. Okay, so we actually used Cauchy integral formula in a very simple manner to compute this integral. Let's kind of look at a slightly more complicated integral to evaluate in the next problem. Evaluate the integral of z square plus 1 by z into z square plus 4 dz over gamma, where gamma is the circle of radius r around the origin. And now the question is to check the cases when 0 is less than r less than 2 and when r is greater than 2. So in these cases we will have to evaluate this integral. We will see why these cases are being described separately when we solve the problem. So what is it that we are trying to evaluate? Let's have a look at the problem again. We would like to evaluate z square plus 1 by z into z square plus 4 over gamma. This is what we want to evaluate. So before we start evaluating it explicitly, let's try to write it down as a sum of partial fractions. So this is going to be, in that case, z square plus 1 by z into z square plus 4 will be written down as a by z plus b by, notice that z square plus 4 is z plus 2i into z minus 2i. So this is going to be z plus 2i here plus c by z minus 2i. And as you can see, 2i will form the points 2i and minus 2i are going to create problems. So the circle of radius 2 is going to be contentious. That is one reason why r greater than 2 and r less than 2 was being considered. Of course, z is equal to 0 is immaterial. We will come to all that in a minute. Before that, let's just quickly solve what a, b, c would be. We get that a times z square plus 4 plus b times z square minus 2zi plus c times z square plus 2zi. Away from the points 0, 2i and minus 2i, this is going to be equal to z square plus 1. And because of that, we can conclude that a plus b plus c is equal to 1. A plus b plus c times z square is equal to z square, and we have c minus 2i times c minus b is equal to 0. So we can throw out the 2i, c minus b is equal to 0, and finally 4a is going to be equal to 1. These are the three equations we have, and with the three equations above, we have a is equal to 1 by 4, b is equal to c, and therefore a plus 2b is equal to 1, which implies b is equal to half into 1 minus 1 by 4, which is 3 by 8. So this is precisely what we will be getting for b and c. B and c are equal. Therefore, if you look at the integral of z square plus 1 by z into z square plus 4, this is going to be equal to 1 by 4 times the integral over gamma of 1 by z dz, that's the first term, plus 3 by 8 times the integral over gamma of 1 by z plus 2i dz, plus again c is 3 by 8 integral 1 by z minus 2i dz over gamma. So this is precisely writing the integral as the sum of these three terms. Let's now consider the case when our curve gamma is a circle of radius r for r less than 2. Let's draw a picture to capture that. We have our origin here, there is 2i here, and there is minus 2i here, and we have a circle of radius r somewhere like this. Now let's get back to the integrals that we are trying to compute. If you notice, 1 by z plus 2i, 1 by z plus 2i and 1, okay, let's focus on this. 1 by z plus 2i is holomorphic on C minus the point minus 2i, right? It's away from this point that I have I'm just going to mark in green. This function is going to be holomorphic, and notice that on C minus 2i, the curve gamma of t equal to r e to the power it for r less than 1. This is null homotopic. It can be homotope to the constant curve at say 1 is null homotopic. And by the Cauchy's theorem, we get to conclude that integral of 1 by z plus 2i over gamma is equal to 0 by Cauchy's theorem. Similarly, the integral over gamma of 1 by z minus 2i is also equal to 0 by Cauchy's theorem. So, the second and the third terms here, they vanish when we apply the Cauchy's theorem in the case when gamma has radius less than 2. So, we only need to worry about 1 by 4 integral of 1 by z dz over gamma. This is the only thing we have to worry about. We could either use a direct computation to compute this, or we could use the Cauchy integral formula to the constant function 1 and conclude that this is going to be the constant function 1 evaluated at the point 0. So, this is going to be 2 pi I times 2 pi I by 4 times 1 by 2 pi I integral of the constant function 1 by z minus 0 dz. This is equal to 1 at 0, which is equal to 1. So, this answer is going to be pi I by 2. That is precisely the answer when r is between 0 and 2. So, hence when 0 is less than r less than 2, the integral over gamma of z square plus 1 by z into z square plus 4, this is going to be equal to pi I by 2. Now, let us see what happens when our radius r is greater than 2. Let me capture that with a pink line, a pink circle. So, this is going to be the r now. That was a circle, but anyway. Now, we will do the same trick as we did for 1 by z and apply Cauchy's integral formula to all the three. When r is greater than 2, by the Cauchy integral formula, (3 by 8) times the integral over gamma of 1 by z minus 2i dz. This is going to be equal to 3 by 8 into 2 pi I times 1 by 2 pi I integral over gamma 1 by z minus 2i dz. Now, I will leave it as an exercise for you to sit down and check that this particular curve is going to be homotopic in C minus 2i to a circle of radius r around 2i. Just a straight line homotopy. Maybe I should just write it down. Let epsilon greater than 0 be small enough. I generally not written down the homotopy saying that it's a straight line. Most of the homotopies we have dealt with were straight line homotopy. So, it was very easy to write it down. Nevertheless, let me do it here once. Epsilon be small enough so that, well, the 2i comma epsilon bar is contained in D0 R. Let's take such an epsilon. So the picture is this. We have a circle of radius, the disk of radius R, there is 2I here, and we are looking at a small circle of radius epsilon. And let gamma 1 be equal to 2I plus epsilon e to the power it for t gamma of t, for t in 0 to 2 pi. Just define h of s comma t to be equal to 1 minus s times gamma of t plus s times gamma 1 of t. What is that? This is just going to be a straight line homotopy of this type. So this is the point along the straight line. Okay, maybe. So the green lines are going to capture the homotopy. It will be like this. So notice that we would like our curve gamma to be homotopic to gamma 1 in C minus the point z0. In this case, z0 is 2I. So if you look at h of s comma t in this manner, this is precisely what is being captured. These are the straight line homotopies that we have. And by applying the Cauchy integral formula, integral over gamma is going to be equal to, this is going to be equal to, hence 1 by 2 pi I integral over gamma of f of z by z minus 2i. So f of z in this case is just 1 by z minus 2i dz. This is going to be equal to 1 by 2 pi I over gamma 1 by z minus 2i dz. And that's just going to be by the Cauchy integral formula f evaluated at the point 2i. But again, f here is the constant function 1. For f equal to the constant function 1 by the Cauchy integral formula, this is equal to just 1 evaluated at 2 pi, which is equal to 1. So let's go up and check what we have established. We have established that this quantity is equal to 1, and therefore we are ending up with a 3 by 8 times 2 pi I. Hence 3 by 8 times the integral of 1 by z minus 2i dz, this is going to be equal to 3 by 8 times 2 pi I, which is equal to 3 by 4 times pi I. Similarly, we will have 3 by 8 times the integral over gamma of 1 by z plus 2i dz also is equal to 3 by 4 times pi I. The argument for 1 by z minus 2i over gamma, 1 by z over gamma is not going to change, and therefore 1 by 4 times the integral over gamma of 1 by z dz will continue to be equal to, what did we calculate, pi I by 2 or pi I by 4? That's going to be pi I by 2, and hence integral over gamma of z square plus 1 by z into z square plus 4, this is going to be equal to pi I by 2, and both of these will be 3 pi I by 4. So this is going to be equal to plus 3 pi I by 2, which is equal to 2 pi I. That's the answer. So for r greater than 2, this integral is going to be equal to 2 pi I. Notice that we used Cauchy integral formula in a very crucial way in this problem in both the cases, when r less than 2 and r greater than 2, to get hold of our answer. Notice that the most key aspect in this problem was to identify what curves were homotopic to what curves and how they were relevant to this problem. So that's one key thing one has to keep in mind when we solve these kind of problems. In the next problem, let's use Cauchy's integral formula directly to get hold of a proof of Liouville's theorem rather than invoking Cauchy estimates. Let's try to get hold of Liouville's theorem directly. The problem, however, is not to directly get hold of Liouville's theorem. Let's see what the problem is. Let f be an entire function. And a comma b be complex numbers such that a is not equal to b. Let r be greater than the max of mod a comma mod b. Then evaluate the integral in, which is equal to the integral f of z by z minus a into z minus b dz over gamma, where gamma of t is equal to r e to the power it for t in 0 to 2 pi. Okay, capital R e to the power it for t in 0 to 2 pi. Further, evaluate limit n going to infinity of in. So I missed a very crucial condition here. So let me add the condition of boundedness. Let f be a bounded entire function. That is how Liouville's theorem is going to come into the story. Let's see. So what are we interested to compute? We are interested to compute integral f of z by z minus a into z minus b over gamma, where gamma is the circle of radius capital R around origin. The standard trick will be used here. Let me just quickly write that down. This is going to be equal to the integral of 1 by a minus b times f of z by z minus a minus f of z by z minus b dz. This is precisely what we will get by writing it down in terms of partial fractions. So this is again going to be 1 by a minus b times the integral over gamma f of z by z minus a minus 1 by a minus b times the integral f of z by z minus b dz. And interestingly enough, this is going to be equal to gamma is a circle of radius r around the origin, and by a very similar argument as in the previous problem, this is going to be homotopic to a circle of radius epsilon around a for epsilon small enough. And because of Cauchy integral formula, one can directly write this to be equal to f of a. So there is a 2 pi I that will feature in 2 pi I by a minus b times f of a minus 2 pi I by a minus b times f of b, just by a very similar argument around b. Notice that capital R is greater than mod a and mod b both. And this is going to be 2 pi I times f of a minus f of b by a minus b. So Cauchy integral formula tells us exactly what in is going to be equal to. Okay, so the problem is actually written down a little incorrectly. This is not what we would like to see. We would like to evaluate when r goes to infinity. That's what we would like to evaluate. What happens when r goes to infinity? Notice that till now we have not used anything about the boundedness of our function f. Now let's try to compute limit as r goes to infinity of in. Notice that f is bounded implies that mod f of z is less than or equal to m for all z in C. That's the first observation. And therefore, if you look at absolute value of in, what was in again? Absolute value of integral over gamma of f of z by z minus a into z minus b dz. And if you notice, when a and b are fixed, this absolute value f of z by z minus a into z minus b, this is less than or equal to m for mod z, and remember that this is also mod z minus a is greater than or equal to mod z minus mod a, right? So this is greater than or equal to r minus mod a, and similarly mod z minus b is greater than or equal to r minus mod b, and therefore 1 by absolute value of these, that is going to be less than or equal to r minus mod b into r minus mod a. This is because of this, and hence we have absolute value of in is less than or equal to m by r minus the absolute value of b times the r minus the absolute value of a, and the arc length of gamma, which is 2 pi r. Therefore, if you look at the limit of in as r goes to infinity, this is going to be less than or equal to the limit as r goes to infinity of m 2 pi m by 1 minus 1 minus absolute value of b by r into r minus the absolute value of a, which is equal to 0. Therefore, we have the limit is equal to 0. Hence, limit as r goes to infinity of the absolute value of in is equal to 0. But we already calculated in every stage, at every stage. You notice what was in? In is actually equal to this. So we have, although we have completed the problem, one more step is going to tell us what Liouville's theorem is going to be. If you notice, this implies that at every stage in is 2 pi I times f of b, or rather f of a minus f of b by a minus b, and we have just checked that this is equal to 0 for all a and b. So once you fix a and b, this is always going to be satisfied. This implies that f of a is equal to f of b. This can be done for any two choices of a and b in the complex plane, which implies that f is identically equal to a constant. Notice that this is exactly the conclusion of Liouville's theorem, that if f is a bounded entire function, then f is a constant. That's something which we were able to conclude from this problem as well after solving it. Let's look at another application of Liouville's theorem. This is over. Let f be an entire function, such that the absolute value of f prime of z is strictly less than the absolute value of f of z for all z in C. Then prove that there exists a positive real number a such that absolute value of f of z is less than or equal to a times e to the power mod z. Let's look at a proof of this. What do we have in the hypothesis? We have that we know that f mod f prime of z is strictly less than mod of f of z, but that tells us that the absolute value is a non-negative number, and that tells us that mod of f of z is always strictly greater than 0 for all z in C. This implies that f does not vanish in C, and hence g of z equal to f prime of z by f of z is an entire function. But what do we know about g of z? We know that absolute value of g of z is less than 1 for all z in C. That is good, because now we will apply Liouville's theorem to the entire bounded entire function G. By Liouville's theorem, G is identically equal to some constant C for C in the complex numbers. So, what do we have? This implies that f prime of z is equal to C times f of z. Okay, let us now use the fact that f is also an entire function. Because it is an entire function in the entire complex plane, we will be able to write a power series expansion of f centered at the origin. Since f is entire, recall that we gave a power series expansion. We proved that f is analytic, complex analytic, and therefore if R is such that dz0 R bar is contained in our domain omega, in dz0 R we have a power series expansion around z0 which converges to f. Now, when f is entire and if you pick the origin for any radius r, if you look at dz0 R bar, that is contained in the complex plane, and therefore we will have a power series expansion in the entire complex plane. By looking at every possible r, we have a power series expansion in the entire complex plane. Since f is entire, there exists a power series expansion f of z equal to summation a n z to the power n in C. Now, that is good because in the disk of convergence, we know that f prime of z, this is going to be equal to summation n a n z to the power n. And what we have just concluded is that, and since f prime of z is equal to C times f of z, we have summation n a n z to the power n is equal to summation C times a n z to the power n. Oh, z to the power n minus 1. I am sorry, there is a slight mistake. So, let me be a little careful. This is from 1 to infinity. By equating coefficients, we have C times A0 is going to be equal to 1 times A1, which is A1. C times A1 will be equal to the coefficient of z to the power 1 here, which is going to be 2A2 and so on. We have C times AK is going to be equal to K plus 1 times AK plus 1. And inductively, we will be able to hence conclude that AK will be equal to C to the power K times A0 by K factorial. This is something which you should sit and check. We will be able to conclude something like this. And therefore, we know exactly how our f is going to be. F is going to be equal to summation a n z to the power n, which is equal to a0 times summation c to the power n z to the power n. So, this is cz to the power n by n factorial, and this is equal to a0 times e to the power cz. In fact, we have explicitly computed what the expression for f is going to be. I will leave the rest as an exercise for you to check that absolute value of f of z then will be less than or equal to some positive number a times e to the power mod z. That is going to be straightforward. In fact, we now have a very explicit expression for f. In the next problem, we will show that if our holomorphic function is bounded, if an entire function is bounded by a plus b times mod z to the power k, then it is necessarily a polynomial. Let me write it down. Suppose f is an entire function such that absolute value of f of z is less than or equal to a plus b times mod z to the power k for all z in C, where a, b and k are positive integers. Then f is a polynomial. So we will use a variant of the Cauchy's estimates. Let's fix some point z0 in the complex plane. Let z0 be in C. Consider the circle of radius r around z0. Let gamma of t be equal to z0 plus capital R e to the power it. And what is our higher order Cauchy integral formula telling us? Notice that we have a bound on f of z here. So we will be wanting to use that somehow. So let's look at fk plus 1. That's something which will change it if this is not what we are interested in. Let's see what will happen if we consider fk plus 1. This is going to be equal to k plus 1 factorial by 2 pi I times the integral over gamma f of z by z minus z0 to the power k plus 2 in this case dz. And let's now take the absolute value. Remember, this is exactly how we were going towards Cauchy estimates. Yeah, notice that if mod f of z is less than or equal to a plus b times mod z to the power k for all z in C, this would imply that mod f of z is less than or equal to a plus maybe a prime plus b prime times mod of z minus z0 to the power k for all z in C. This is something which can be easily concluded using the triangle inequality. I'll leave it to you to get hold of this inequality, and once we have this inequality, what will happen to the right hand side here? In star, we have absolute value of k plus 1 by 2, k plus 1 factorial by 2 pi I times the integral over gamma f of z by z minus z0 to the power k plus 2 dz. This is going to be less than or equal to the bound on the integrand. So the k plus 1 factorial will survive by 2 pi. The thing above is going to be bounded by a prime plus b prime times r to the power k, and we have in the denominator r to the power k plus 2. This is what the function, this function is going to be. And we still have the arc length, which is going to be equal to 2 pi capital R. This is precisely what our bound is going to be. So this is why I said it's going to be a mild variant of the Cauchy inequalities. So this is going to be less than or equal to k plus 1 factorial by 2 pi into a prime. So 2 pi's will cancel off, so I can forget about the 2 pi, which is good. And then this is going to be a prime by r to the power k plus 1 plus b prime by r. So as you can see, the choice of k plus 1 was correct. So what do we have? We hence have, this is true for every r. So f k plus 1 of z. So hence, by taking r going to infinity, we have absolute value of f k plus 1 of z0 to be equal to 0. This can be argued at every point z0, and hence this tells us that f k plus 1 is identically equal to 0. Now, f is an entire function, and this implies that f L is identically equal to 0 for all L greater than or equal to k plus 1. What do we have? That means that f of z, which is summation a n z to the power n, has a L equal to FL at 0 by L factorial, which is equal to 0 for all L greater than or equal to k plus 1. This is in C, right? It's an entire function after all, which tells us that f of z is equal to a0 plus a1z plus up to ak z to the power k, and that's precisely what we had set out. Recall that the identity theorem, which was a stronger version of the principle of analytic continuation, it stated that if a function f defined on omega vanishes on a set which has a limit point, then f is identically equal to 0. The precise statement that we proved was that if f of z0 is equal to 0, then there is a small disk r around z0 such that in the punctured disk f does not vanish. These are equivalent. The next problem is to find a function, or the question is this: can we get hold of a function in the unit disk which vanishes on a countable set? Does there exist a function holomorphic on D such that f of Zn is equal to 0 where Zn is a countable set in D? Let's think about why such a problem came up. If you are having a countable subset of D, the question that can be asked is, does it necessarily have a limit point? Because if it does have a limit point, then the identity theorem directly tells us that f is going to be identically equal to 0. So in particular, if our Zn is contained in some disk of radius r around 0 for r less than 1, then in particular this countable set would be contained in D0R bar, which is a compact set. So countable set of distinct points. Let's put it that way, countable set in D consisting of distinct points. So if we are focusing our attention on a closed disk of radius r where r is less than 1, this will have a limit point, because in a compact set, such a countable set of distinct points will certainly have a limit point. So we will certainly not be able to get hold of such a sequence. If at all there exists such a sequence, we will not be able to get hold of such a sequence contained in a disk of radius r where r is less than 1. In particular, we will be able to get hold of such a sequence only when the sequence converges to the boundary mod z is equal to 1. So this example tells us that it is possible to have a countable set in D of distinct points and a holomorphic function f where such that the function vanishes on this countable set. Let's look at a solution for this. Consider the following sequence: Zn equal to 1 minus 1 by n times pi. Notice that as n goes to infinity, this is a sequence which is converging to the point 1. So in particular, this is not going to be contained in any compact subset of the unit disk. And now define our function. Zn's are all distinct, right? And define f of z to be the composition of the sine function with 1 by 1 minus z. So notice that 1 by 1 minus z is a function which is holomorphic on the unit disk, and sine is an entire function. So the composition is certainly going to be a function which is holomorphic on the unit disk. And the question is, this is not going to be a constant function. That's something which you should sit down and check. Then sine of then f of Zn, what is going to be f of Zn? This is going to be equal to sine of 1 by 1 minus Zn is 1 minus 1 by n pi. So this is 1 minus 1 by n pi. By after all the computations, this is going to be equal to sine of n pi, which is going to be equal to 0. So we have explicitly constructed a function which actually does vanish on a countable set. But notice that in the unit disk, this countable set does not have a limit point. It is a discrete set. You pick any Zn, identity theorem still is satisfied. One can get hold of a small enough epsilon such that in d Zn epsilon, our function f does not have any other 0. Let me stop here.